Okay, let's crack on then. If I can just welcome everyone to our webinar day 2, Intel webinar series. Obviously, we'll host this in partnership with Intel Software and Bain Core. I know most of you attended yesterday's, so I'll keep the intro quite brief. Obviously, this is the second session. We're going to be showing you how to introduce heterogeneity to legacy applications. My name is Daniel Payton. I'm the Intel Software Licensing Specialist here at Grey Matter. And I think we skipped the slide, just going into a little bit about Grey Matter. I hand you straight over to Stephen so we can move on with his presentation. Obviously, if you do have any questions about who we are, feel free to reach out. We're going to have some of our details at the end, same as yesterday. So I will hand straight over to you, Stephen, and you can crack on.
So we're looking at introducing heterogeneity to legacy applications using Intel oneAPI. As I said yesterday, I'm Stephen Blair-Chappell. I work for a company called Bain Core, but nearly all my work is Intel based. So still very much active with Intel in different projects. This is the second of 3 sessions. There's another one tomorrow. Yesterday, we looked at how to take your Parallel Studio code and move them on to using Intel oneAPI. And in particular, we focused on a few things around what things you could use a classic compiler and so on. And I'll do a very quick sort of 1-minute refresh of that. Today, we're looking at, introducing heterogeneity to legacy applications. And then tomorrow, we'll be looking at using, OpenVINO and looking at how to use that with using CNNs and so on. Okay, a quick recap from yesterday. I'm actually going to just go to my diagram, my bit of paper again. So let's get that. So yesterday, get a few things out of the way. Got the paper there, yeah. Yesterday is a different scenario today. Yesterday, the scenario was that you have a piece of code that you've been using with Intel Parallel Studio, and we took an example of maybe you've got 3 sections. The diagram might look different to yesterday, but I'm just trying to go over the concept of what we were doing yesterday. And the goal yesterday was to take the Parallel Studio code and move it across to using oneAPI. And the way that I proposed that it was done is that any parts of code which are vectorized or highly optimized or used in benchmarking, then it's better to keep that on the classic compiler, but the other parts could go over to the new LLVM-based compilers. So, and that was a sort of strategy yesterday. So this became, let's see if we can get this right. We had C and A. Okay, I know the boxes are not the same shape. And then B. And what would happen is that this part, which is the vectorization part, this would use still use a classic compiler, so ICC or iFort. But the other parts of the code, because they're not depending on the vectorization unit and maybe a lot of hand tuning that you've done, then these could be built using the new compiler. So that would be ICX or IFX, for example. So that's both of these. So what you had here is trying to move as painless as possible across using oneAPI. But at the same time, any parts that you identified as being optimized, vectorized, and so on, then the recommendation was that keep that part to use the classic compiler, which is also shipped with oneAPI, so identical to what you have in Parallel Studio. Today, we're doing something a bit different. What we're doing today, so if you notice here that there was just one part that stayed on the classic and the rest moved across to the to the new compilers. Today we're doing something a bit different. What we're saying is that we've got, let's say, a really huge project, okay, with lots of parts to it, which is currently on Parallel Studio. But what you're interested in doing is to introducing offload to this legacy application. Now, the applications may be similar or very different, but it's likely with a big project, it's a lot more complex in terms of your build environment and so on. And what the recommendation in this case is, and the purpose we're doing this, sorry, is because if you have your system with CPUs, then you might also have FPGAs connected, or you might have some sort of embedded HD graphics, or you might have a GPU and so on. The intention of moving across to, I'll write it up here, to oneAPI in this instance is you want your big project to just run minimally and well. But what you do is you're interested in offloading some part of your code to these new things. So what would happen is you'd choose a bit, which is a candidate for offload, and this is the one that we'd try to get to run this way. And to do this, then you'd either have to use the ISX or IFX, in other words, the LLVM-based compilers. But the rest of your project, so that's this bit and this bit, which maybe you wouldn't benefit from any offloading, what you do is you keep those with the IPSXE. Well, not with IPSXE, sorry, you keep it with the classic compiler, so ICC and iFort. Likewise, so both blocks, so the other block as well, yeah, okay. Yeah, it goes that way. Both use, so these are using the classic compiler, and this one is using the new LLVM-based compilers, because it's only the LLVM-based compilers that support offloading. Can you see the difference between the yesterday and today? So yesterday, most of our code eventually would have gone across to the new compilers, apart from the vectorized part, which we want to preserve some hand optimization that you might have done. So you've got only one little part using the classic. But on this second scenario, which is today, what we're saying is, imagine you've got a huge project, you don't really want to move anything really, you just want it still to work, move it to the oneAPI environment, but keep the majority of it still using ICC and iFort. So all your command line options, all your different code, everything works identical. But what we do is we find parts of that project which could be offloaded onto an accelerator. So the motivation, this is the motivation, getting the code here, but not touching any of the other. And for most big projects, that will be one of the motivation reasons for using oneAPI. So that's eventually this side and this side might end up merging into some other diagram as you work through into a next stage of a project. Let's go back to the slides. No, that's not the slides, is it? Let's go to the slides there. And I think what we'll do is we'll do that as well. Okay, so that's the what I was talking about yesterday. And you learned yesterday that the reason that we're able to do that mixing is because for the classic and the LLVM compilers, the objects are binary compatible. I gave some diagrams on the strategy for yesterday, but we'll just skip past that one. So what about today? An acceleration strategy. What I'm suggesting is that there are 4 or 5 steps. I put 5 here because I put an extra step in brackets at the end, but it's 4 steps. So the first thing you do is to move your Parallel Studio project to oneAPI, but continue to use the classic compiler. Just make sure everything builds the same. The next step is to find what loops would benefit from offloading, and we're going to use a particular tool to do that. We'll demo that now. Then you'd implement the offloading part. So that means changing some of the code in the bit that you've identified as being suitable for offloading. And then after that, you'd start doing some further profiling. And then as a last further step, you might also want to consider how the previously vectorized code is being used. But actually, I do want to go back to my diagram for one instance, because there's something that I realized. So previously, the vectorized code had stayed with the classic. In this new, bigger project, we're recommending that everything stays with the classic except for the bit you're offloading. So it could be if within your project you've got some highly optimized code, well, that by default in this approach would perform equally well in the new environment. Of course, it might be later on, after our fifth step in that diagram, this you may decide is suitable for offloading rather than staying on the classic. Okay, so let's go back to the diagram. We used the Intel Dev Cloud, and I'm not going to go through the Dev Cloud, but these slides are for your reference. So talked about that yesterday. 2 ways of connecting. One thing I like, which I didn't point out yesterday about the Dev Cloud, is that if you go using Jupyter Notebook, there will eventually come a time when the notebook times out. So you're given typically, I think, about an hour's access on a Jupyter Notebook session, and then it stops. But a window comes up that says it's not running, and there's an option to restart. And I found that a really convenient, and I must say lazy way of just keeping, easily connecting and reconnecting to the Dev Cloud throughout the day. Okay, there's some links there, again, which I gave last week, both for getting started on the Dev Cloud and some training modules. The hardware that's available on the Dev Cloud would be, there's a CPU, GPU, and FPGA. There's a whole series of scripts. So normally, as I said, you can either work interactively, use a Jupyter Notebook, or request an interactive session, but normally you submit job scripts. The next few slides show some job scripts. Again, I'm not really going to talk through those. So let's just go straight past those. Okay. But what I will do is this last slide, you can query what kind of nodes are available on the Dev Cloud. And so what I'm going to do is just have a go at that. So what I'll do now is switch to my other computer, and hope the mouse is working. Yes, good. And let's start Dev Cloud. Okay, and then let's get down to where we are. So I normally go to the Get Started. And then launch Jupyter Lab. Good, and we'll launch server. Just wait for a moment while it launches, and then I shall go into just onto the command line and just do a few things. Looks like it's a bit tired today. It's a bit slow. As I said yesterday, that don't put the Dev Cloud as being a strategic component in your development work, because there are days when it just might not be available, might not be working properly. And it's looking a little bit like that today. I have a backup plan if the Dev Cloud isn't working. We'll just give it another second, but it should have come up by now. So it probably means there's a problem. So the dev cloud is hosted in the US. So it's likely that if there are any issues overnight, or at least in the mornings, UK time, there's probably no one there to attend to any errors. They're probably quite wisely all in bed, I would think. So, okay, looks like the dev cloud has died. So let's do my alternate strategy. What I'm going to do is the machine I'm working on here is a Windows machine, which I was logging on to the dev cloud. What I'm going to do is, this is a dual boot machine. I've actually got Linux on here as well. So I will restart. While that's restarting, let me go back to my slides for a minute. Okay, so we're not going to do this, but when you get onto the dev cloud yourself, you can check what kind of nodes are available to see which ones have got GPUs, CPUs, and so on. But we're not going to demo that now if the dev cloud is down, which it appears to be. So we're looking onto our 4-step strategy, and when my machine is rebooted, which won't take very long, then we'll run the examples locally on my machine here. So the tool that we're using is, it's the advisor, it's the Intel advisor, it's the vector advisor, and it's got facilities for modeling offloading. And rather than showing it in slides, I'm going to show you it live, and then I'll run some scripts. Let me just show you so what I've got is a set of scripts. So the way it happens is that you take your application, you use Advisor to do a survey. So this is step 1 on this slide. The survey, it does a profile, but it also collects some other information beyond the normal profiler. Once it's collected that information, it then runs you then run a second run of the tool to be able to count how many iterations each loop is doing. That information is merged together. At the same time, we tell the advisor we're interested in a particular set of devices. So in this case, it's a Gen 9, so it's an embedded HD graphics on a fairly recent laptop, for instance, and so on, or a workstation. Having done that, you then have to double check that any loops that are operating in your code don't have dependencies on each other. So in order to, as you probably all well know, for code to be made parallel, whether that's on a GPU or on a CPU, then that one loop mustn't depend on another loop. So the loops in a piece of code can be executed at the same time. So that you can do a performance analysis. In our demo, we're not going to do that. We're going to skip that step. We're cheating, but you should do that as well. And then the final step is then to model what the speed up would be if we ran the code on this device on Gen 9 in this case. So let me go back. Let's see when my computer is. It's expecting me to. Hopefully it will start. Yeah. Okay, back to the slides just while that's doing its stuff there. So let's go back to here. Now, all the scripts that I've used in my example can also be captured by using the GUI, and we'll do that in 1 or 2 minutes. Okay, and having done that, we're then going to go on to looking at looking a little bit at implementing the offloading. So let me go back to see whether my PC has come to life. Good, it has. So this is my local Linux box. It's literally just under the table I'm sitting on. It's a fairly new sort of workstation. It's not overly powerful. It's a 1-socket system, but it's got the latest Xeon processor in. But it's an I think it's an i5, no, it's an i7 that's in it. I can show you the exact one. And I've already installed the tools, but already in this system. So first thing we're going to do is open the terminal. And what I'll also do is, let's make that bigger. I also forget which button it is. Let's try that one. Okay, I'll have to do it this way. I've forgotten the hotkey for zooming into here. Right, it's Control++. Okay, let's try that. Oh yeah, I see, it's that one. Okay, and I think we'll probably put me down there for a minute. What I'll do is I'll maximize this so you see the benefit of it. I've already installed oneAPI on here, and it also sources the file to set up the environment. So you can see all the different tools are already available. So let's do Control L. And I've got a particular example. Let's have a look. First thing I'm going to do is show you the spec on the computer I'm running. So if I do an ls-cpu, and what you'll see here that, okay, I think I keep moving myself around. We'll go back a bit. What you can see here is there's support for AVX2, but there's no support for AVX512. So this is an i7, I think. Let's go up. Yeah. So this is Intel Core TM-i7. If I'd got an i9, there are some i9s that have support for AVX512. And also, in fact, one of my laptops that's sitting to my, in fact, this laptop I'm showing my slides on, that is an i9, and there's on there, you can actually use things like DL Boost. It's got support for AVX512, but this workstation with my Linux on hasn't got that, but it's still a fairly recent machine. Okay, and so what we have here is we've got 16 CPUs. Okay, well, 16 cores is what it really means. Okay, so that's the spec of the machine. So what I'm going to do is do our example. So we get 2. So what we're doing is we want to do some offload analysis. I've got a particular example here, and it's a matrix multiplier. It's nothing complicated at all. So let me do a quick look at the code. Let's do. So if I scroll down here, you can see it's nothing fancy at all, but for the purpose of using the profiling tool to find out what offload would work well, that would be good. The code actually works. It's designed to use doing 2 lots of calculations, so matrix multiply, and it compares if you offload, it compares the offload version with the version running on the main machine, and it comes up with a passed if it's passed. So what I've got here is the version that we're running here. So it's just triple nested loop, nothing complicated at all. But as I say, it fits perfectly for what we want. So let's come out of there. Let's do I'm just going to take my picture off for a minute. It's getting in the way too much. So what I've got here is first a build. So let me show you what the build will look like. So all I'm doing is calling the LLVM-based compiler. I'm using -G to say create some debug information, and it's creating an executable. So why don't we do that? It runs, it builds RAR, that's fine. We'll run it. We'll just show you what the run script is. It's just calling the executable that's being called. So do that. When I run it, it does nothing more than say passed. And what that's doing is it's running 2 versions of the matrix multiply, it gives you the option of putting some. I've got a lot of noise coming in here. Let's see whether we can get rid of that. Give me 1 second. I'm just going on to the Zoom to see if anyone. Give me a second. Right. Just having a look on our attendee. Give me 1 second. Okay, it's just everyone's muted, so it must have been just background noise. Okay, so carrying on with this. The code has passed. What we're trying to do is to do an analysis. So we're going to look at the code and we're going to use the advisor offloading advice to see what our performance would be like. So let me just show you the script I'm now going to run. So what this is doing, it's a somewhat complicated script. It's doing the 4 steps that I talked about a short while ago in one of the slides. First of all, we're doing a survey, and this is calling advisor, and it just collects, it's like a standard profiler, but it collects some other information in relation to vectorization as well. We then do a second run, which does this uses instrumentation to collect the trip counts. And the reason we do this twice is because first time when we run the survey, it runs at about, there's very little overhead. So the runtime is probably, maximum 5% longer than what it would be if you hadn't done the survey. So that gives us our real-time information. When we do the trip counts, then the advisor uses binary instrumentation to do a count of every loop iteration, because one of the things that you need to work out in making your code parallel or offloading it is, are there sufficient loops that it can be made, it makes sense to be parallel. So that's the thing we do here. At the same time, we also feed in information about what version of the what device we want to offload to. And in my case, if I just go to the top here, then I've set this this variable to the Gen 9 GT2. We might try another version after we run it. Having done the trip count, say which will take longer, but since our application is running ever so briefly, then this will not take long anyway. And then the next step is that you would check to see if there are any loop dependencies. This again relies on instrumentation, binary instrumentation. So the tool is looking at every access to memory within each iteration of the loop. And if it sees that the memory location in one loop is being accessed in another loop, then there's a dependency. But the code I've got, there are no dependencies anyway, so we're skipping this step because this is quite time consuming. This could make your program, if you did it on 10 times slower. We certainly don't want to do that, but we know, so we're skipping that step, but it's there just for your reference, so you know how to do it. And then the last step is we actually do the modeling of the offload on the GPU that we gave when we called the trip count. And what we're also saying is we put an extra option here. And we're saying is there are no dependencies. This is what this option is saying. It's that we've made an assumption. You can make the assumption there are no dependencies. Okay. Having done that, we'll then be able to look at the results. So let me just clear the screen a bit. So we're now going to run the third one. Okay, so that's going to run for a few minutes. First part's quite easy. Just to remind you that I've got a break for coffee timetabled, which I think is going to happen in about 6 minutes time, 10:43, I think. So just to alert you to that. So we'll have a short break for coffee at that point. Okay, so it's now doing the trip count. If you notice, the first time it ran, it was less than a second, the time to run it. This second time, now it's the trip count's using some binary instrumentation. It will take a bit longer, but I don't think it takes a huge time in this example. Let's see how quick we can just wait for a second. While that's happening, let me just drop back to my slides for a moment. Once we've found a place that we would benefit from offloading, and we'll go through that process, then we would implement a solution. If you're, you have choices here. So if you're looking at, well, we're working on the basis that you've got an existing project and it's a legacy project. So in that circumstance, it's going to either be C, C++ code, or it's going to be or Fortran, maybe OpenCL, although I'm not focusing on OpenCL here. I'm not focusing on the CUDA here, but if you were wanting to port CUDA across, you could also do that and use a tool called the compatibility tool. That's not a topic for today. So what I'm looking at is that you've got, really it's the middle two, you've got an existing program, which may or may not have oneMP, but it's written in Fortran or C. So what we're doing is we're running Intel Advisor and we're looking at the offload advice. And once you've done that, then if you're doing a C++ program, or you've got already, then the way to add your offloading would be to use data parallel C++. If you are working with Fortran or C code, then the way to add the offloading would be to use oneMP. If you're not if you don't consider C++ to be a friendly programming environment, then you need to use the oneMP solution for doing the offload. But if you're really comfortable with C++ and your code's already written in C++, then using the data parallel C++ is the way to introduce the offloading. Let's just see how far our profiling's gone. Let's go back to our machine. Yeah, everything's run. So we've done a run, and what this will do is it will generate a set of results. Now I'm going to have to browse into the results. So I'm going to go here. I'm going to explain more of this with the Advisor tool in a while, but let's go straight to the results. So we're in Home DB, oneAPI, there, for offload analysis. There's a projects directory. Now, one of the, I think this is something that needs correcting. The results of this profile is buried completely in the subfolder. When you're using the GUI version of the tool, you can get straight to it, but otherwise it's really is way down in the cellar, as it were. And there are many things that are generated. There are some CSV files which you could bring into so a spreadsheet program or whatever if you wanted to look at the values of the different bits of collection that they've done. But what I'm interested in is there's two files here. There is a program tree.dot. This is a file that you can create with GraphViz, and it shows the calls that have been made on the acceleration. There's also a PDF version of it. And then the third thing is this report.html. The first thing I'm going to do is to look at the report.html, which I've double clicked on. So I'm hoping it'll, yes, open up. I'll maximize this so we see it at its best. So what happened here is that we said that we were interested in Gen 9 T2, so that's the configuration that's being used. And what Advisor did was it's used the combination of the 4 steps to provide a what if, not a what if, but a speculation on how the different loops would behave if they were offloaded. And what the tool will do is it takes your main loops and then it calculates a speed up. And it may also give a reason why a code couldn't be offloaded. In this case, my code can be nicely offloaded. Okay, at this point, I've just got the alarm coming up saying coffee machine here. Okay, so good. I hope you all had a good break, a bit of fresh air or whatever. Let's carry on. We finish in just over, let's see, 40 minutes time. So let's carry on. So we've run the advisor. We're looking for the loop that that's going to be a good candidate for offloading. In your programs, there may be, I'd imagine it's much more complicated, but the offloader, the offload advisor will give all the information that you need. And you can see here the summary. Let's first of all get rid of me, and let's make this to be the biggest it can be. That wrong way. Oh, that obviously is the biggest. Okay. Let me just do one other thing, just to make the viewing better for you. I think there's an option here on my, yeah, that hopefully just makes it slightly better for you. And just double check where. Okay, right. So here is the summary, and it gives you can see which parts of your program offload successfully and what are the limitations. In our case, let me see if I can zoom in. This is we're looking on a browser anyway, so I should just be able to zoom in on the browser. Yeah, that makes it probably one too many there. So if you look on the offload side, then the thing that's limiting our offloaded code is it's how the code is being handled in the L3 cache. So that's the last level cache. So it's a bandwidth, it's the amount of data that we're doing. So there are no other issues that are affecting the code that we've written. If we look on the left-hand side, the program metrics, then the original time was 0.7 of a second. If it gets offloaded to the Gen 9 device, then it would run at 0.14, which is an obvious speed up. And what the further information here is that it says here number of offloads 2. And the reason is that because we've got 2 loops that are worth offloading. So I've got a first loop. I'm actually doing a matrix multiply twice in my piece of code. So that's the reason why it says 2. And then it gives the limits on what the speed up can be. Okay, there are some other tabs which are of interest. So we're going to the offload region. There's a significant amount of information in this table. And if I scroll to the right, I'll try and do it slowly. So first of all, we've got information about the loops being offloaded, the estimated speed up, okay, how much time it would be on the target, total execution time, the amount of memory, or how much time is being taken up by the bandwidth in terms of seconds. And then there's information about the last level cache, how that's the access to that, how much time is being spent in that area. Okay, and if you see we're going on and on and on, let's see if there's anything else which is interested. It does a calculation of what the offload cost would be, what the cost of transferring data would be, Now, if you had an application that ran for longer, some of these values that say 0 would be filled. Just scrolling slowly to the right, see if there's anything else. We've got the trip count, so the loop that was being offloaded, both cases ran for 512 times, which makes sense because that's the limit I put in the code itself. Okay, and you see there's a huge amount of information that you can get from there. And what the tool will allow you to do is also to dig into the call stack. So if we go into if you had non-offloaded regions, sorry, you could see that all our regions were offloaded, so there's nothing there. You can also go into the call tree and follow up and down from where you're going, and it will display the appropriate piece of code. So this is the code that was offloaded. Okay. Information on the configuration. So this is the configuration that it used in the background. And you see there aren't really any values in there, but you could add, there is a file that you can edit to add values here as well. And then there's the log file, which just the messages that were sent as it was running. Okay, what I want to do is to just go back to my slides, and then I want to show you something on the tool itself. So let me go back to the slides. Okay, so I was talking earlier on about saying you could either use C or C++ or Fortran, and you'd then choose to either use oneMP as your offload mechanism, or you'd use data parallel C++. Whichever method you use, you've got three challenges. One is offload the code to the device, so so it will run. Secondly, the associated data needs transferring to the device as well. And then the third thing is you'll also need to make that code run parallel on the device. So it's three distinct steps, and both the data parallel C++ and the oneMP have both got mechanisms for doing that, and we'll see ever so briefly those mechanisms. Just a word about the GPU we're using. I think it's a Gen 9 we're using, but here's an example of a Gen 11 embedded graphics. And the graphics, so the GPU has a slice and something known as a subslice. Let's see if I've got a diagram of that. Yeah, here we are. So in the case of Gen 11, there is only one slice, but the whole of the collection there is a slice. And that slice is split into subslices. In this case, there are 8 subslices. And each of these subslices are independent of each other. You can't synchronize between the two sets of subslices. They've got independent memory and so on. Within the subslice, there are a number of execution units. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8 execution units in each subslice. And in the execution units, there are a couple of arithmetic logic units, and then also there is some thread control. And in the case of the Gen 11, I think there's, I think it's 7 or is it 8? It can store, I think, manage up to 8 threads. So you get a parallelism within each of the execution units, which is managed by those thread states. And as the program runs, then the execution units or the thread control will be changing the state to the different threads, which in turn are using the 2 arithmetic logic units. So there's a great degree of nested parallelism. And then even with the execution units or the arithmetic logic units, you've got these very wide SIMD registers. So you can have more than one calculation being done in a single cycle. So you can see here that there are nested sort of parallelism within the device itself. Oh, come on, there we are. This is the different spec of the different graphics, embedded graphics that's available, and also there's a discrete graphics card. So the latest device available is on the left here, the first column. That's the Iris Xe, and that's a DGPU, a discrete graphics device. It's has a separate card that you can put into your workstation and so on. The other three devices here are all integrated GPUs, so they're within the silicon of the CPU. And you can see, if you look down third row up from the bottom, the architectures. We looked at Gen 9. This in the sampling, the slide I showed you previously was Gen 11, and then there are other versions as the XE versions as well. So it's newer generations of the GPU architecture. Okay, so I'll go back to the, let me go back just, I'm going to skip. The demos that we've got, you have a choice of, on implementation, of doing two kinds of code. And I've got slides here that describe in a little bit more detail about the code. But what I want to do is to be practical and go back to the lab itself. So two things I want to show you. First of all, I ran my profiling, the advisor offload, by using the command line, because it was designed to run on a server without graphics, and then you collect the results and look at them elsewhere. But the question is, well, how do I get that information? And you can do it within Offload Advisor, and we're going to try and do it here. So let's see if we can get to the home. I'm doing this, sorry, this is just, I'm being silly here. This is just a HTML file. Let's run the GUI version. So so we're using Advisor. Okay. Let's just minimize this a bit. Actually, give me 1 second. I've lost the bottom of my screen here. Let's do that. Right. So I'm running the graphical version Advisor, and the thing I want to show you just in the next 3 or 4 minutes is how you'd I just need to let someone into the Zoom session. Dan, if you're on, if you can hear me, can you let Leanne in? She's in the waiting room. Thank you. So what I've done here is I've started my GUI. So it's here. Let's maximize it. And what I'm going to do is create a project. We'll just call it test. Such an exciting. And there are different kinds of survey of the different projects you can do. And what we're interested in is doing an analysis. So okay. Just looking for it myself. It's the bottom one here, the performance modeling. Yeah, so we want to do a dependency analysis. Now, the reason I'm showing this is for one reason only. If I'll just say okay for a minute. And you have options of different kinds of projects. We're going to do the offload modeling. So if I click on there and when I open it, there's no data at the moment. On here, as part of the GUI, let's see if we can just make it a bit bigger. Let's see if that does anything. Then the 4 steps I had as scripts are also here. And if you click on each of those, so on the survey, and then press this third button, it gives you a command line option. Now, I've not put in the name of the application in my project yet. This is all a bit small to see, isn't it? But the thing I want to show you is that when you run the GUI version, you're able to capture the command line for each of the 4 steps. So so the first one was doing a survey, the second one was doing a trip count. So again, if I went on there, if you can see it, it's rather small from here, and so that's how you get the command line from the different tools. You can also view the results in here and do, but we're using the HTML to view it. So I'm going to close this. That's all I wanted to show on the tool itself. So let's get rid of that. And back to here. What I want to do is to go on to the implementation side. So what you do so far is you've identified loops that could be offloaded with the offload advisor. You then say, right, I need to implement my loops. Now, in the time that we have, we've only got limited time to look at the implementation, but I want to show you a couple of tricks. And that is, we go, I've got here an empty folder. And I want to show you that if you want some examples of implementation code that you can experiment with yourself, there is a oneAPI command line interface that allows you to build some projects. So this, and since I was showing the example on some vectorized code on a matrix multiply, there is a matrix multiply example available. Let me show you what I mean. So if I go oneAPI CLI and enter, what that does is it connects to a set of projects on GitHub, and you can create new projects from the command line. You can either be C++, Python, or Python. I'm going to go C++. I just want to show you a very simple data parallel C++ example, but it's also got openMP as part of it. It's a matrix multiply. Maybe I should just scroll down the screen and show you some of the examples. So just back to the top a bit. So there are toolkit examples. So with the toolkit, you've got the direct programming, and I'll scroll down, and there are some different examples. So that's direct programming, writing in C++ or using data parallel C++ mainly. The other way, if you're working on FPGAs, there are some separate examples, tutorial examples. Keep scrolling down. If you're deciding to use the libraries, so there are some libraries that you can, again, try some examples. What I want to show you is the tools one. So at the bottom, there's also some examples for doing advisor. So you can do the matrix multiply. There's an example for using the debugger. And then if you're working on IoT, there's some examples there as well. Okay. This migration one is an example of taking some CUDA code and then changing it to using oneAPI. So you might find that a useful one to look at. And then a Vtune at the bottom. So let me scroll all the way back up again. What I want to do is to get the matrix multiply one. And so it's this one here. Right. So what we've done is created a matrix multiply. So what I want to do is to show you a couple of examples. So let's have a look at the files. Let's go to the source. So we've got 2 examples, one openMP and the other data parallel C++. So let's do the matrix multiply one first with the OMP. So this is the example. Again, it'll look subtly different to the example I used before, but extremely similar. But what we have here, it's almost identical to the one I used earlier, actually. Except for this is C++, whereas mine was C. Then what we have here is looking looking for the relevant code. I'm just scrolling down. Right, this is the bit that we want. What we have here is the matrix multiplication. Above it, we've got a pragma statement. And this pragma statement, which I've got more information on the slides, shows several things. First of all, it uses a pragma OMP directives, and within that, it makes the code both parallel and offloaded. And it's using, there's the pragma OMP target is the one that does the offloading, and then there are various extras in that construct that we've written there, which make the code parallel. And rather than describing it on the code here, I'll just show you on the slides. So let me go back to the slides. And I'm just quickly going to go down to the oneAPI. I've got some data parallel C++ slides here as well, which are first, but I'm actually going to skip through those. So here's an example of a piece of code. It's just with C code that uses the oneAPI. I'm just going to show you the extra parts that are added to make it to be offloaded. So we've got pragma OMP target. What this does is that the code that's within that for loop will get offloaded to the target. And the way that you would build that is with the line that you see at the bottom. So ICX, this is using the LLVM version of the C compiler. In order to enable oneAPI offloading, you need both the FI oneAPI and also the target SPIRE64 option as well. And what that does is that creates a fat binary, which has got both binary code for the CPU and binary code also for the offload. Okay, let's go on to the next bit. This example here is just showing the more comments on the previous part. Okay, so this code that we've got here, we've got the issue over making code run on the target, but also it running, having the appropriate data. And what's happening here is that the arrays are copied across at the beginning of the oneAPI, at the beginning of the directive, and at the end of the directive, there's an implicit synchronization at the end of the curly brace, and the data's copied back. But actually, some data doesn't need to be copied back. So what you can do is you can use some extra words in the directive. So we've got this map directive. So, and you can say that the data just needs to be copied to the device, or it needs to be copied to and from. So by adding the map here, we're reducing the amount of data that's going onto the device. So we're beginning to handle the data. So this code will run on the target. It will copy all the data that you need, and it will copy back the results, but not any unnecessary copying. For a full parallelism, then what you need to do is to use the parallel for. If you look here, we've got two nested pragmas here. We've got the OMP target map, so that's pushing the code and the data onto the device, and then within that pragma, we're then using oneAPI parallel for. So that will make the code to run parallel, okay, on the device. But what will happen is that I showed you the example of how the GPU works, and this code will only run on one subslice. So the other subslices will not be running any code. You need to do something yet further in order to spread this parallel code across the different subslices. And this is the way it works. There's a construct that's called teams. And when you use that, then it creates a team of teams, if that's not too confusing. So in this example, and then when you use the parallel for as well, then your loops end up being split onto a team of teams, which in turn are also parallel. And each one of those teams run on a different subslice. So that's how you get the nested parallelism. So here's the complete example. Okay, so the teams create the multiple team of threads, and then you use the distribute to distribute the work amongst the different subslices. Okay, so with that, so here's the final example. I think we've got everything in here. So that's taking advantage of both threading and also, I think there's one of the, yeah, that's the last slide I've got here. What I want to do now is to go back onto our computer for 1 second. So we looked at the code. Also in this code, there is a data parallel C++ version of the code. So let's have a look. So we'll just quickly look at the matrix multiply deep C++. And here we again have to deal with the same issues. So it's getting the code onto the target, making sure the data is handled correctly, and there's the appropriate level of parallelism. And if we go down here, there are two things to point out here, and I'll show it in the slides. There is a queue created in this code. Let me just see if I can find just a fraction further down. Bear with me. Yeah, here we are. The queue was declared earlier on, but the queue is associated with your accelerator, with the device. And what you can do is that you can submit code to the accelerator via the queue. And here we're using a method of, so this is a lambda instruction. So I think lambdas came in C++ 11, I think. So this is like an anonymous function, as it were. And what you're able to do is the code that's within the lambda will get executed on the device itself. I've got slides that explain that a bit more. This method is using a programmatic way of getting data in and out of the device. And you see these things called accessors. So this piece of code here is saying, is using accessors that are going to be to access the code that gets onto the device. So if you have a look, when the code is submitted, there's access to the code, and then the results at the end, the results can be read back by the same accessor. So the values are put into the data, it's submitted to the queue, the code is executed, and then when it's finished, then you can read the results back using accessor. There are two techniques for handling data. This is a very explicit way using buffers. In my slides, I've got a different version. Let me just come out of here then. What I should do is at least run the code. So I think it's make run. So let's do make all, first of all. This builds the data parallel C++ version of the code. See, it's calling the data parallel C++ compiler, number of warnings, something's not unrolled. And then if we do a make run, what this is doing is calling the code. Oh, it says there's an internal error with LLVM. I may not have the right driver on my local system here for the to support that. Okay, anyway, let's now go back to the slides for a second. Just keep an eye on the time, we've got 10 minutes left. Wrong one. So what we have, we've seen an example using oneAPI. We've just looked at a piece of code that uses data parallel C++. So let me just quickly go back. So data parallel C++ is an extension to C++. It's based on the Cronus sickle. And what you see is the code that you eventually use, that was it can exist all in the same file. I think, well, I'll put myself back on. Here's an example of a piece of code. So let's just go back one. So we have host code and then accelerator code and then host code again. The accelerator code was the code that was in the Lambda function, showed you in the other code. So here's the example of the Lambda function. You also have buffers and accessors to pass data in and out of the device. So there needs to be a mechanism to get the data onto the device. This is the method that was used in the source code that I just showed you. You have a queue for submitting. The queue is, each queue is associated with a specific device, and only one device. And there are different selectors available. That's on the left. There are examples where you can have selectors for CPU, GPU, and so on. And on the Intel Dev Cloud, there are more complex examples and training which shows you how to use those. Now, the previous example had an explicit way of handling the memory, having buffers. There is an alternate version, it's an extension which is being provided by Intel, and that is to use something called unified shared memory. So this example looks much more friendly in that it uses pointers, it uses a special malloc, and then it looks extremely simple. If you compare it to the previous version, which you've got all the buffer stuff happening, that gives you a finer control over what's happening. But it may be that you prefer to use the unified shared memory, and where you can, in your code, use a special pointer to be able to access code both on the host and on the device. In this case, we've got the kernel itself in this piece of code here. It's still using a Lambda function, and at the end of the Lambda, the queue parallel for, we put a wait for the kernel to complete, and then we get the results. And in this case, the code is allocated dynamically. Okay, so that was the two methods of implementing. Once you've gone on to that stage, and I'll just go past the oneMP versions, then you'd look at profiling and tuning. On the Dev Cloud, there is an example of profiling with Vtune that I would have liked to have shown you, but since the Dev Cloud has more or less died, that's unlikely. Maybe we'll, no, I won't get involved in trying to run it now, because we'll probably end up just watching paint dry when it tries to run. So with the profiling, you could use Vtune. Here's an example of doing a Vtune collection. So this is a profiling tool which works similar to the profiling tools that you might know, like gprof and so on. You could collect everything from the command line and then get Vtune to generate a HTML report and then view the report itself. Now, what I'm going to do in the last 2 minutes before I need to be winding down is to, let's see if we can just run a Vtune example. So let's see. I think we've got the 4 there. Just clear that. Let's get rid of me again. Right, in this folder, I've got some similar examples. This is now using a different example. It's an ISO 3 DFD example. I've got some slides on it. It's also well documented on the Dev Cloud. What I'm going to do is to quickly build it, just to show you that this is being built with data parallel C++, and everything's been built. I'm not going to run it. I'm going to go straight into profiling hotspots, but I'll cat the command. So what we have here is a script which what I'm doing is I've got a variable which I'm saying, just setting different kinds of different profiling that you can do. And in this case, I'm just profiling for hotspots. And if you, this is what I'm doing. I'm calling Vtune collect, and the type, the collection type is what's been set here. And you'll get copies of this code as well. You can experiment trying different ones here. So let's actually just do a let's do profile hotspots. And what this will do is it'll run Vtune. And okay, I haven't set my system up here. Okay, we're not going to do it on here. I need to edit a particular file, but since we've only got 5 minutes left, we'll give that a miss. What we can do is, let's have a look at the Vtune data, see if I've collected one earlier. I can't remember if I have. I think I have hotspots. Okay, I'll tell you what I'll do. Once you've collected the data, you could actually look at it from Vtune. So why don't we do that? Let's just make sure I've got the right place. Yeah. Do it. Okay, while that's loading, I'm going back to my slides, and then I'm going to come back to that for just 2-minute conversation. So back to the slides. No, that's me. And we might as well put me back on. Okay, so you can collect the, when you come to the profiling stage, then you can collect all your data and then view it locally, or you can generate a HTML file. The example that we're about to profile, but it wasn't set up correctly, but I've got a result I ran earlier, is an ISO 3DFD example. It's a stencil code, and that's the main code. And what we're doing is that we're looking at what the performance is. There are examples of this that's running on Data Parallel C++, and then you can see what the behavior is using Vtune. Okay, with that, I'm going to say just quickly that our next session, it's not Wednesday, March the 24th, it's tomorrow. Don't travel back in time, I won't be there. We're going to look at using convolutional neural networks coming from the, it's the optimized version of Intel Python and the OpenVINO. So that's very much looking at getting a model that's an AI model that's already been trained, maybe code that's built for recognizing objects or something, and then we're looking at how that can be optimized and run on low power devices or run on PCs. So there are various optimization techniques to do with deployment of trained models. So it's the inference part of AI. If you're not really into AI, it's no problem. It will still be a useful thing for you to join us. Okay, I'm coming to the end of what I'm doing. I did want to go just in the last minute to one slide. I've opened up the Vtune Profiler, and what it's done is it's given me a set of summary results already, and it's telling me what the overhead is and so on. If we'd had more time, we could dig through this and you'd look at where, is the dependency the way that you'd like it to be. But what the Vtune will do is that there are lots of different profiling options as per the script I showed you a while ago, and you can even look at how the GPU offloading is doing. Okay, with that, I'm going to stop, and I'm going to hand back to Dan, who's going to wave goodbye to us.
Yeah, so just a really quick wrap up here. Obviously, if anyone has any questions, feel free just to pop them over to me in a quick email, or directly over to Stephen if you do have his details, and we can get those answered for you if you didn't get them wrapped up today.